guys, today we'll be looking at argand diagrams. So we'll be looking at how to show a complex number on the argand diagram, how to find the modulus and argument of a complex number, and how to write down a complex number in modulus argument form. So let's begin with argand diagrams. These are quite similar to the Cartesian grid. So this represents a two-dimensional plane. If you're watching this on a screen, which is 2D, you can represent any point on your screen with a set of coordinates, x and y, relative to some fixed origin. An argand diagram is quite similar, except on the x-axis we have real numbers, and on the y-axis we have imaginary numbers. So let's say we want to represent some complex number. A complex number is a sum of a real and an imaginary number, so we can write it in the form a plus bi. If you're unsure about this, you can watch my previous video on it, but a complex number is made up of a real part and an imaginary part. So this could be any imaginary number like 6i, 2i, minus I, and this is a real number like integer, decimal, irrational number, and the sum of these forms a complex number. So let's say, for example, we want to represent the number 3 plus 2i. This is a complex number. It has a real component. The real part is 3, and the imaginary part is 2i. So let's see how we'd show this on the argand diagram. So since we've got 3 in the real component, I'm going to go 3 units along on the x-axis, which is the real axis, and we have positive 2i plus 2i, so I'm going to go in the positive direction 2 units on the imaginary axis. And this point on the diagram represents the complex number 3 plus 2i, which has coordinates. We can write it like this. So a complex number x plus iy we can represent on the argand diagram with coordinates x, y, or as a vector, a column vector of x and y. So this represents the units along the real axis, and this represents the units along the imaginary axis. Now let's say I want to plot the sum of two complex numbers on an argand diagram. Complex numbers 4 plus I and 3 plus 3i, and I'm asked to plot the sum of these. Let's first plot the two complex numbers. So 4 plus I, I'm going to go 4 units along the real axis and 1 unit along the imaginary axis. So z1 is here. And for z2, I'm going to go 3 units along the real axis and 3 units along the imaginary axis. So z2 is here. Now, let's actually evaluate what the sum of these two complex numbers is. If you're unsure how to do this, my previous video on this is linked in the description. So the sum of these we add the real components, so 4 plus 3 is 7, and then we add the imaginary components, so that gives me 4i. So 7 plus 4i. Let's mark this on our argand diagram. So 7 units along the real axis and 4 units along the imaginary axis. So over here is the sum of these two. Now what you'll notice is the vector that goes from the origin to the sum is actually the diagonal of a parallelogram which has vertices z1 and z2. So instead of computing the sum this way, I could have just drawn this parallelogram to find the sum. The reason this is the case is because when you add the two complex numbers, you just add their real parts and then add their imaginary parts separately. So you can see that if I add 3, let's go back to our complex numbers, we had 4 and 3 in the real parts. So if I do 3 and 4, that gets me to there. And if I add the imaginary parts, which were I and 3i, we end up at this point. Or in other words, this vector is the same as z2, but just translated by 4 to the right and 1 vertically, which is z1. So to summarize, the vector that goes to the sum of two complex numbers is the diagonal of a parallelogram which has those two complex numbers at its vertices, where the origin is also a vertex. Now let's look at the modulus argument form of complex numbers. So the modulus of a complex number is the distance of it from the origin. If we were to draw that complex number on an argand diagram, the distance of it from the origin is the modulus. So once again, let's draw an argand diagram. If I have complex number, let's say 4 plus 5i, this length in red, that length is the modulus. And we can work this out using Pythagoras' theorem, because I can go along 4 units to the right along the real axis and go up 5 units. So to find the length of that hypotenuse of what is a right angled triangle, I can just do the square root of 4 squared plus 5 squared. So to generalize, if I have a complex number on the argand diagram, which I can write in the form x plus iy, then the modulus, which we denote in this way, is the square root of x squared plus y squared. The modulus is also sometimes called r, or it may be written in this way, but these all refer to the same thing, which is the distance of that complex number on an argand diagram to the origin. Now, the argument of a complex number, so this was the modulus, the argument is the angle it makes on an argand diagram from the positive real axis. Once again, let me draw a diagram. Let's say we have the complex number 1 plus 2i. 1 plus 2i somewhere here. The angle this makes with the positive real axis, so the positive real axis is this side. This angle, theta, is the argument of the complex number. We can write this as arg z. We can work out what the argument actually is by using trig. So if I know the size of this base is 1 and the height is 2, because the complex number was 1 plus 2i, so we've gone along 1 unit in the real axis, positive real axis direction, and positive 2 units on the imaginary axis, then I can use tan of theta, which will be the opposite over the adjacent, so 2 over 1. So tan theta is 2, and I can use the inverse tan to find what theta is. So to generalize this for any complex number in the form x plus iy, to find the argument we can just do the inverse tan of y over x. An important thing to note is that this argument is typically given in the range negative pi to pi. Here we're measuring the angle in radians. Pi radians represents 180 degrees, and 2 pi radians is 360 degrees. So this is like negative 180 degrees to positive 180 degrees. When we give the argument between this range, it's known as the principal argument. So let's say a complex number lies over here. Let's say our complex number is minus 3 minus 2i. So we've got negative 3 units along the real axis and negative 2 units along the imaginary axis. Here's my complex number. You may work out the argument from the positive real axis as this angle, but since the principal argument is always between negative 180 and positive 180 degrees, or minus pi and positive pi radians, this angle is definitely bigger than 180 degrees. So really, if we're looking for the principal argument, we want this angle. So to find that angle, we can find what this angle would be using the fact that this height of this triangle in red, the height is 2, because we went negative 2, and the length of this base is 3, because we had minus 3 along the real axis. So we can find that angle in red. this one, and then we can take that away from 180 degrees to find this purple angle, which is the principal argument of that complex number. Now let's see how to represent any complex number that we have in this form in modulus argument form. So let's once again draw an argand diagram. But let's say we have the complex number x plus iy and the coordinates are xy. Now if I draw the modulus, which is this length, and also draw the argument, which is the angle it forms with the positive real axis, and let's draw a line from the complex number down to the real axis perpendicular to it. This length right here is the modulus, which I'm going to write with the letter r. This length along the base of this right angle triangle is x, because it represents the real component, and the height is just y, because that's how many steps we've gone up along the imaginary axis. Now let's use some trig. If I write down cosine of theta, in terms of this right angle triangle, cosine of theta is the adjacent over the hypotenuse, so that gives me x over r. Now let's do the same for sine of theta, which is the opposite over hypotenuse, so y over r. Now rearranging these to make x and y the subject, I'll end up with x equals r times cos theta, since cos theta was x divided by r, and I'll end up with y equals r sine theta. So if I substitute these into my complex number, I end up with r cos theta for x plus I times, let me move this to the side, plus I times r sine theta. So I've just replaced what we found x and y to be in terms of r and theta, just replaced them into the form of a complex number. So I'm going to take out the factor of r from both terms, and we find that we can write a complex number in this form which has the modulus r and the argument theta. So once again, r is the modulus or the distance of that complex number from the origin when we draw it on an argand diagram, and theta is the angle it makes from the positive real axis on an argand diagram. The reason why this modulus argument form is quite useful is because there are a couple rules we can use to multiply complex numbers quickly when they're given in this modulus argument form. So let's take a look at those. So let's say we've got two complex numbers, z1, and I'm writing these in modulus argument form, and z2. So r1 is the modulus of the first complex number, r2 is the modulus of the second complex number, and theta1 is the argument of the first complex number, and theta2 is the argument of the second one. In order to multiply these two numbers quickly, what we can do is just multiply the moduli and add the arguments. So we have this rule that the modulus of the product of two complex numbers is just the product of their moduli, and the argument of the product of two complex numbers is the sum of their arguments. Let's see why this rule holds. So let's actually multiply these two complex numbers. I'm doing z1 times z2. This equals r1 times r2 times by this times by this. I did this step because all of these four things are being... I did this step because all of these four things are being multiplied by each other, so I've just rearranged the order in which they're being multiplied. Now let's multiply out these two brackets. So I have r1 times r2 at the front, and now cos theta 1 times cos theta 2 plus cos theta 1 times I sine theta 2. I'm going to put the I at the front. Plus I sine theta 1 times cos theta 2 plus, now we have I sine theta 1 times I sine theta 2. I times I is I squared, which is minus 1, because if you remember, I is the square root of minus 1, and if I square it, I will just get minus 1. So here I've got minus 1 times sine theta 1 times sine theta 2, which I'm just going to remove this and write a minus sign, because I was adding negative 1 times all of this, which is the same as just taking away. Okay, now let's simplify this a bit more. So we have r1 times r2. I'm going to group together these terms and then these ones separately because they have an I in them. So we have cos theta 1 Now I'm going to use the trig addition identities, which I'll put up on the screen right now, but that will help me simplify this bracket to cos theta 1 plus theta 2. And the second bracket, so this bit, will simplify to sine theta 1 plus theta 2. And we had r1 times r2. So if we now compare this to the modulus argument form of any complex number, which looks like this, we can see that the modulus is just the multiple of the two complex numbers moduli that we multiply together, and the argument is the sum of their individual arguments. Now there's a similar rule for when we want to divide two complex numbers in modulus argument form. So for two complex numbers, the modulus of z1 divided by z2 will just be the modulus of z1 divided by the modulus of z2, and the argument of z1 divided by z2 will just be the argument of z1 minus the argument of z2. And there is a similar proof we can write down for this. I will link it down below. Let's actually multiply two complex numbers. So we're going to go through an example of multiplying two complex numbers in this modulus argument form. So let's say I have, so the argument is in radians, 5 pi by 12. And z2 is 4. And we want to find z1 multiplied by z2. So to find the modulus of z1 times z2, we just multiply their moduli. So here the modulus of z1 is 3, the modulus of z2 is 4. So this will just be 3 times 4, which is 12. Now let's find the argument of z1 times z2, which is the argument of z1 plus the argument of z2. The argument of z1 is 5 pi by 12. The argument of z2 is pi by 12. Adding these, I get 6 pi by 12, or pi by 2 if I simplify this. So that tells me the argument of z1 times z2. So let's write down this in modulus argument form. It will be 12, since 12 was the modulus, times cos pi by 2 plus I sine pi by 2. I hope this helped. Thank you so much for watching, and next time we'll be looking at regions on the argand diagram and loci.